Hello, here's a video on the design of steel connections to support out-of-plane bending moments. Now, in the UK it's normal practice to join rolled steel sections such as these I-beams using a mixture of welds and bolts. Typically the welding takes place in the workshop and the bolting takes place on site. Here you can see that this beam is coming into a column and it has a series of bolts through a welded end plate. So the end plate is welded to the beam and then the bolts connect the plate to the column. Each of these lines represents 2 bolts. So this connection has 2, 4, 6, 8, 10 bolts in total. Now imagine that this beam was bending downwards. It's got a bending moment applied to it, and as that bending moment is applied to it, this whole connection is going to want to rotate, and there's going to be a mixture of tension in the bolts and compression at some point in the connection. Okay, another example where this could occur, and here is a typical portal frame shed under the worst case loading of dead and live load acting on the roof rafters. When that dead and live load acts, the shed tends to sort of kick out. Its knees, if you call these its knees, they kind of bend at the knees, and this joint here, it tends to close up. So as that's closing up, there's a bending moment because there's some rotation taking place. So this joint, here it is, typically it's strengthened, and here's some of the strengthening. This is a haunch, the little dashed lines show that there's a weld, and then we've got some bolts. Now as this joint tends to close, there's a tendency for there to be compression at one point and tension in the bolts. Now I'll try and illustrate that with a nice cheap and cheerful working model. But here we go. Here's a beam connected to a column. It's got a welded end plate, and there's 1, 2, 3 lines of bolts. Now generally the bolts come in pairs because an I-shaped beam, you can fit bolts on either side of the beam. Now as this beam tends to rotate round, if I apply a bending moment on it so that it's bending, then what it's going to do is it's going to start to rotate about a point which is its stiff point, and that stiff point is going to coincide with the very center line of the bottom flange, and it's going to rotate as the bending moment is applied, and these bolts are going to be stretched. Now assuming everything stays straight, can you see that some bolts are going to be stretched more than other bolts? And the amount that each bolt is stretched is simply in proportion to its distance from the point of rotation. Great. So let's have a think now about how we can actually calculate the forces in the bolts. And the way we can do that is by considering a connection. This connection's got 4 bolts in it. Bolt rows B1, 2, 3 and 4. It's got a bending moment applied, and the rotation is going to take place around a certain point, and that point is going to be where the center line of the flange, that's the stiffest point, coincides with the interface of the connection. So that line in between the column and the end plate coincides with the center line of the flange, and that's the point of rotation. So what's really important is we know the distance of each bolt from the point of rotation. Now if the first bolt is subjected to a certain strain, that strain is directly proportional to the stress, and as long as the area is constant, then that stress is going to lead us to the tensile force within the bolt. So if we say that that bolt has got a tensile force of Ft kilonewtons, and it's at a distance y1 because it's B1, then the next bolt down, B1, is going to be in some kind of ratio to the distances, and it just so happens that the force in bolt row B2 is going to be Ft times y2 divided by y1. So it's in proportion to these distances. Same goes for bolt row B3. It's ft times y3 divided by y1. Okay, so it goes all the way down to the bottom, and we can surmise that the applied bending moment is going to be exactly equal to each of these forces times each of these distances. So there's 2 rows of bolts, so the bending moment is going to be equal to 2 times, when I've opened the brackets, the force in the first bolt times its distance to the point of rotation, plus the force in the second bolt times its distance to the point of rotation, plus the force in the third bolt times its distance, and so it goes. And eventually you can work that through with a little sleight of hand of algebra. So it's a little sleight of hand of algebra, and you get to the equation that the force in any bolt is the bending moment that's applied to the connection times the bolt's distance to the point of rotation divided by the sum of all the other distances to all the bolts squared. Okay. Now let's have a look at an actual connection. So here's a beam, it's connected to a column. These bolts are set out as follows. So 90mm between these two, 90mm between these two, and 300mm down to the centre line of that bottom flange. Great. There's a force, 350 kilonewtons applied to this beam, and it's at a distance 350mm from the face of the column, which is the interface. Now the whole thing is going to rotate around this point here. So what I want to do first is work out the distances of the bolts, and then I want to work out the sum of all these distances squared, and then I can work out the forces in all the bolts. But before I do that, I'm going to work out the bending moment. So this is an outer plane bending moment because the plane of the bolts is in line with the end plate. So that's the plane of the bolts, and there's a bending moment that's pulling that out of its plane. So this is the plane of the bolts, and the bending moment is cranking it out. So I'm going to have to get the shift on. Let's see. So the bending moment is going to be the force times the distance. That's going to give me an answer of 122,500 kilonewton millimeters. It's a strange unit, but it's actually quite useful for connections to use kilonewtons and millimeters. So for bolt row B1, what's its distance in millimeters? Well, it's going to be 300 plus 90 plus 90 is going to take me from centre line to the bolt, and that all adds up to 480. What's that squared? That's 230, 400. Bolt row B2, that distance is going to be 390. When I square that, 152, 100. Bolt row B3, that distance is simply 300. Square that, 90,000. So the sum of all the y-squareds is going to be this lot added up together, which gives me 472,500 times 2, because the bolts are in pairs. In total there are 6 bolts. 2, 4, 6. Add that lot together and it gets me 945,000. That's going to be in millimeters squared as it happens. Okay, now what I want to do is I want to find out the force in the top bolt. So the force in the top bolt, so for B1, F is going to be my over sigma y squared. So for B1, F is going to be m 122,500 times y 480 all over y squared, 945,000. That gives me an answer of 62.2 kilonewtons. Now I can do the same for B2 and B3. using a different value of y in each case, and that's going to give me values of 50.6 kilonewtons and 38.9 kilonewtons. Now what's nice now is that all of these bolts are in tension, and you could argue that they're all pulling to the right hand side as that beam cranks down. Each of the bolts is in tension and they're pulling towards the right hand side, but there's a compressive force here pushing to the left hand side. Well, that compressive force must exactly equal all the sum of the tension forces, or the whole thing won't be in horizontal equilibrium. So the compression force acting at the point where the bottom flange is simply going to be the sum of all of these other forces. So the compression force is going to be 2 times 62.2 plus 50.6 plus 38.9, and that all comes to 303.4 kilonewtons. So in a very short space of time I've worked out the tension force in each of the bolts and the compression force, which may cause local buckling or buckling of the web in the column, and I can design my welds accordingly. Great, that's the end of that. I hope you found it helpful.